Welcome again. Today we look at topic 13.2 for IB Chemistry, colored complexes. Looking specifically at this example where a solution of ammonium hydroxide is added to copper sulfate. Here you can see ammonium hydroxide is being added to copper sulfate. A bit more, and then you can see a precipitate forming, copper hydroxide. And then even a bit more, and then a complex of ammonia, water, and copper. And the color goes from this light blue to a much darker blue. But what is the reason for all of this? Well, let's think about it. In copper sulfate, you've got the copper ion and the sulfate ion in aqueous solution. And when ammonium hydroxide is introduced, hydroxide ions associate with copper ions to form the precipitate, here shown as a solid, copper hydroxide. But with the addition of excess ammonium hydroxide, then this tetraamine complex is formed, where 4 ammonia ligands and 2 H2O ligands associate with the d orbital system of copper, which is a transition element and which has 3d orbitals capable of associating with these ligands. When these ligands associate with the copper d orbitals, the orbitals are split in their energy level, and this is what leads to the change of color. Let's first begin by looking at the electronic configuration of copper. Argon core 3d10 4s1. But the Cu2 positive ion loses 2 of these electrons to exist as argon core 3d9. To explain these color changes, it's important to understand the layout of the electrons in the d orbital system of copper. The 9 electrons arrange themselves over the 5 orbitals with 2 in each of the 4 orbitals, and finally, in the 5th, just 1 electron. But to fully appreciate the reason for the color change, it's important to grasp the spatial arrangement. And here you can see the 3dz2 orbital system. And the ligands which associate with this orbital are the H2O ligands. When ligands associate with orbitals, they energize those orbitals, taking them from the degenerate state or the ground state to a higher energy level. The ammonia ligands associate with the 3z2y2 orbitals, here, raising the energy levels, and this results in a splitting of the energy levels of these 2 orbitals, with all of the orbitals beginning at the same energy level. But in the presence of the ligands, 2 of the orbitals which have associated with those ligands, the dz2 orbitals and the dx2y2 orbitals, have a higher energy level than the other 3 orbitals. So this difference in energy now allows electrons to transition from one state to the next. And when they do this, they absorb energy and they reflect energy. And if the wavelengths of this light are in the visible spectrum, then it results in certain colors, like we saw with the light blue color going to the dark blue color. But it's important for students to visualize how this d orbital layout gives rise to the splitting. And the best way to do this is to build your own model with simple materials that you can find. Let's have a look. We can begin with a block of modeling clay like this one. And then we can put 2 pencils, one at the top and one down here at the bottom, to represent the dz2 orbital. But dz2 orbital is, as you can see, straight up on this axis, and it's made up of a donut shape, if you will, going around here, and 2 dumbbell-shaped lobes above and below. When copper forms an octahedral complex, one of the ligands enters here at the top, and another ligand enters here at the bottom. The other 4 ligands in the octahedral complex, well, they go into the dz2, dy2 orbitals, which we can represent by placing 4 pencils at these 4 locations. One ligand going in at the top, another at the bottom, and 4 of them fitting in here, with all of these 4 areas here making up the dz2, dy2 orbitals. So far here, in the formation of the so-called octahedral complex, it is only the dz2 orbitals and the dz2, dy2 orbitals that are being used. But this octahedral complex only requires the dz2 orbital and the dz2, dy2 orbitals to actually form the complex. But there are 3 other orbitals which exist in the d orbital system of a transition metal like copper. And if we are to explain why the color changes happen, then it's important to know the actual location of these other orbitals. One orbital set is located here in this plane, with one lobe fitting in here and continuing over on this side, and another lobe fitting in here and here. But none of these 2 lobes would be directly in contact with ligands in an octahedral complex. So the influence of the ligand on those orbitals will be less than the influence on these. And so too will be the case, for this is just one plane. If I were to rotate to another plane, then I would be able to get another set of d orbitals. And finally, what about the plane here, in between? That too would form now a 3rd set of d orbitals. But none of these sets would directly come into contact with the ligands as part of the octahedral complex. The only direct contact with the octahedral complex comes from the dz2 lobes and the dz2, dy2 lobes. All of the other orbitals which occupy the spaces between these pencils are not directly in contact with the ligands. And as a result, this leads to a splitting in the energy levels. So why then do the metals have different colors? Well, the explanation for this has to do with the identity of the metal ion. It also has to do with the oxidation number of the metal. In this case, Cu was the metal, copper, and the oxidation number, +2. For in many cases, if the metal ion has no available space in its d orbitals, then it's not going to be possible for electronic transitions to occur from one level to the next. And this all has to do with the identity of the metal, whether it has d orbitals available to begin with, and whether or not those d orbitals allow for transitions. For instance, in the copper electron configuration, there was no possibility of transitions from one level to the next, for the entire d shell was filled. But when you had Cu2 positive, with copper having an oxidation number of +2, then it became possible for an electron to transition from one level to the next. And of course, and very important, it has to do with the identity of the ligand. For different ligands, when they associate with the d orbital systems, lead to different levels of splitting. And related to this level of splitting is the energy gap, which is associated with different colors of light absorbed and reflected. And this is what gives rise to the color. So the identity of the ligand is very important in determining the extent of the splitting. Some ligands lead to more splitting and others to less. So different ligands create different splits, and as a result, different colors. Electrons in the d subshell can split into 2. The d block elements formed colored complexes when excited electrons move from their ground state, like we saw in the example. And the color, the blue color, the dark blue color that was observed, is really due to the fact that the complementary color is the one that was absorbed as the electrons transitioned from one level to the next. And the color that was reflected is the dark blue.